I don't really have any slides or anything like that prepared for this talk. It was more of a exploration of ideas of how to map relational semantics onto a true multi-master, eventually consistent database. And as far as I know, like I've looked at pretty much every project out there, and I can't see anything that does this currently. It's kind of as if you were to take the replication model of something like CouchDB, that is true multi-master nodes can go down, come back up, they resync over time with relational semantics, which is a, people, pretty much all of you thinking about databases, this is a pretty difficult problem to think of, and it introduces a number of constraints about what you can actually do. So it's, like the title said, it's taking the ideas behind what's made some of the NoSQL solutions so popular, and especially in terms of the high availability, and bringing that back to the relational world and seeing how that's done. I've actually started a project to do this. It's called SlackDB. It's very much a very early development project. A lot of the concepts I already have worked out for the most part, but I'm only up through the protocol and DDL specifications for being implemented inside the relational database. A lot of the other stuff I've prototyped out, but I haven't actually gotten working to a fully functional project by any means. And what I want to do is try to just start a discussion around, would this type of database even be useful with the types of constraints that are imposed on it by this type of replication model for a relational database.
So define the problem that we have to discuss, because eventual consistency is a little bit large.
Yeah, exactly. It's a giant piece of chalk. So the idea is that if you have, we'll just work at the table level for now. And how many people are familiar with running a multi-master MySQL setup, for example? Like, and you do the auto increment offset things, and then you hope everything works out, but eventually somebody touches the wrong rows, and then everything's broken and out of sync. You've probably all gone down that path. The idea is to eliminate those problems by introducing a replication model that is both idempotent and deterministic. So regardless of the order of events that you apply them in, and how many times you apply them, you're going to get the same database. And if you can get that type of replication model, everything else sort of sorts itself out. So these are two distributed nodes with the same table, a replica, but rather than having the traditional, right here and, read only here, and then replication simply goes one way, you want to open this up to have basically two write masters. So when you insert an ID here, let's keep these abstract for now. ID2, obviously these are going to, cross over. But if you also introduce ID1 here, and you actually touch the same row, say if we call this, delta 1 and delta 2, two separate changes, at the end of the day, you want to make sure that these have the exact same chain. You don't want to have, the streams cross and this one ends up with delta 2 and this one ends up with delta 1, which is what can happen in pretty much any current relational database right now. So everyone kind of get the basic problem. So the new project that I'm working on, what it does is it first needs a concept of a mostly, ideally it would be completely globally unique ID to identify everything from your databases, your tables, and your, and every row within your data. You want some type of ID to associate with every entity that you can say, this is the canonical, key to get this piece of information. Because the type of resolution that you need within rows, you also need that within databases. Because say if you have, create table X on one write master, create the table X on another write master, and then eventually those two things are going to replicate across, possibly with a stream that is broken and then catches up sinks later. You're going to have an issue of, I have two tables named table X, and now they're going to conflict because they have different data inside of them. But everyone sees like that problem as well. So it's not just a matter of rows. So what I've done is, instead of actually using the table name, you basically generate a globally unique ID when you create a table, and the name is a piece of metadata attached to that ID. So I'll kind of go from the top of how you would go about creating a full database and a table and so forth. So when you say create DBX, it will generate a global unique ID. And it's not actually a UUID, but since everyone knows what a UUID is for the most part, we'll just use that. And we'll just call that UUID1. And there's a name associated with it, which we'll call X, and basically a dropped time, which is actually also a simple UUID. But the UUIDs that I'm generating, it's actually a 64-bit integer, and it's time-based. So there's nothing guaranteeing that it's actually globally unique, but it's probably going to be good enough for most of the use cases.
Depending on the time zones.
Well, just assume it's UTC. Yeah, everything translates down to UTC. So the first 32 bits is second. So we're good from the epoch until 2108, or I forget the exact year, but basically we don't need to worry about it in our lifetime. Yeah, if someone's still using this at that time, we have bigger problems. The next 20 bits is microseconds, and then the last 12 bits is basically random.
Did you evaluate Snowflake?
Yeah. What is Snowflake?
Snowflake is Twitter's version.
Yeah.
Open source project. It uses Zookeeper to get unique keys you start from, and then there's a time declarer as well.
Okay, I'll have to look at that.
It includes like having thousands and thousands of nodes that are all nodes of unique because they have their own IDs for part of the group they're generating.
Okay. Yeah, I went down the path of thinking of every node would get its own unique ID, so it's a guaranteed unique ID within that node.
You can do it from like start time machines, like pretty much the same level.
Okay. Yeah. So the idea is that you have basically 100,000. Or sorry, 1 million, 4,000 unique IDs per microsecond, which is probably enough for most use cases. And in the case where you could actually have a conflict, you can just sort of examine the payload of whatever that thing's associated with and take the largest of that payload for that particular ID. So say, for example, if your row ID was one of these 64-bit integers, and you had the exact same update, or sorry, you had two different updates that somehow you managed to get the exact same ID there, basically take the larger of the payload of that update. So you can still be deterministic even with conflicts. But I'm making the assumption that this is going to be so rare that it's not going to affect end user performance, and that's an extreme edge case that we can still do deterministically, but won't really be seen later on. So those, but after hearing about Snowflake, maybe I'll do that instead. So for now, let's just assume there's some 64-bit integer that we can be mostly globally unique. And the idea is that every database will have a record. So when you create it, the initial record is, that 64-bit integer will be assigned this UUID. And that also acts as the creation time for it. And then we associate the name X, which we got from the statement, and we also have a drop time, which for now is just 0 since it doesn't actually have a drop time yet. And what this allows us to do is if another database that, say the replication stream is down, does this exact same command and it doesn't have this record yet inside of it, it will create the same, basically the exact same database record here, except the UUID will obviously be different because it's generated a different ID. So at that point, you'll have two table X's in your system, between all of the different nodes. But this is going to be a pretty rare edge case. It's a way that we can handle it deterministically, and we want to talk about the canonical representation of X. We're going to use the UUID with either the largest or the smallest creation time. So at least we know we're going to be talking about the same thing, and we can go back later and say like, hey, somehow there were two table X's. And if you're typing like show databases or list your database instances, you could say, okay, the original created one, or the one with, say, the earliest creation time, is X. And then the later one, which will say, let's write out here, to name, same name, and it also hasn't been dropped yet. You could refer to it as, so if you were to list your databases, this would be X. This would say, X.2 or something like that, and then basically a DBA could go in and say, how did this thing get created? We had a bad replication stream. If these are obviously have the same type of content, you could just take the tables in here and merge those and insert those into there. But the idea is that you're creating a database with the UUID, and the name is an attribute, and you can have duplicates of those. And this allows you to have determinism all the way down through your database if you kind of keep replicating this model. Does that make sense? Or did I lose it?
So eventual consistency would mean that the database would either, you're saying it would tell you about the conflict, or it would merge X and X dot?
No. Basically all the conflict resolution for if you were to end up with two databases named X, that would be sort of at least initially a manual process. Obviously, if it can say that, oh, these have the exact same schemas within the databases, we can probably, you could have a feature that automatically merges them to resolve those. But the idea is that you want to be able to have a system so you can have two write masters, and if there's no link between them, you don't want to inhibit writing on those two nodes, at least for the time being. And like when a lot of people think of eventual consistency, they think, oh, it's always going to be lagging behind, it's always going to be slow, and I'm never going to see the view. But the truth behind it is the eventual part is really an edge case when you're in a degraded mode. Most purposes, you're going to have that link up, and it's going to be almost instantaneous. So when I create this database X, it's going to be on all my other nodes when everything's running normally, and I'm not going to ever run into this use case. This is sort of an edge case where things are really out of sync, and for some reason I need to introduce new databases.
Well, in an eventually consistent system, if your application was doing a statement like create DB, it would only do it once at one node in the system somewhere, and then the system would eventually make it consistent everywhere. The type of conflict people usually talk about trying to deal with in an eventual consistent way is the one update, an old update never propagated, and then someone used the node as a master to do a newer update that's newer than that, and now the database has the old and the new, and it has to merge them. And there's some application cooperation in there, in that applications have certain expectations, and creating a DB twice in two different locations, I don't know. It doesn't seem like any sane application would do that.
And they should. Because normally, this other node won't. Go ahead.
So you start off with your in the back, you have just a tab.
Okay.
Because it seems like, this is really cool, but we got a little bit into the weeds on this. You start off by saying that nobody's really approaching this yet. Have you run across Nimbus DB and their MVCC approach?
It's not open source, so I haven't run across the code for it.
Yeah, it's tough to know what he's actually doing.
We were just talking about Jim. So
I would love to see what they're doing. I don't want to work for them.
One might guess that they're using MVCC, given that it's starting.
Right, yeah, one might guess that.
One might guess that.
But one might guess many things, and one would never know.
Yeah.
Especially about Jim.
But yeah, so before
I'd
this,
love to
like,
see it.
you know, I'll just repeat, like, before this scares you off, normally, you know, this is, you know, we'll call this node A and node B. Normally, this would never happen, and this gets replicated, and when you say create DBX here, it's gonna say, hey, I already have DBX because it has this record. This is only when the link between A and B are severed, and we just need some way to handle these edge cases so we don't have a real mess later on. At least this is a somewhat same way to handle the mess.
It seems to me like if it were eventual consistency, x.2, there wouldn't be x with UID 1 wouldn't exist anymore. It would just be x.2. Because it's the newer thing, and apparently some part of the user's application decided that
Okay.
I want to create it again.
Yeah, and maybe this is something where we could have conflict resolution handle this later.
Yeah.
But before we go down that path, the reason why we do it this way is because when we create tables, you're referencing the UUID of the database you're in, not the table. So if you create, for some reason, if you had some weird application, maybe it was running different versions on different sites, and this creates a set of tables that this one doesn't have, you can't automatically resolve that. So going to the sort of the next step really quick, just to touch on that. When you do a create table, let's call this Y, and, you know, so forth. This is basically going to create the same records, except it's also going to have, we'll say UUID 3, say we created on this node, so the database, rather than referencing, you know, creating table, if you say create table x.y, it will actually end up referencing the ID there, not the actual table name. And then it also has the dropped and, of course, the name Y, and of course all the column information and whatnot.
And just to understand what is going on, taking aside the edge case, when you replicate the database X, it will go into the other node as database X UUID 1, or will it have something different?
No, when you say replicate database X, you actually want to say you're replicating database with UUID 1. It just happens to have the name X at that time. So think of, you know, the database in terms of what their the canonical, you know, reference ID is, which is the UID now. It's not the name any longer. The name only comes into play when you want to observe the current state of any database within the system, or the state of your data within the system. It's like, give me name X, like whatever has been replicated to me, that may be this one or it may be that one, depending on who you are within the system, because, you know, that node may be down. Does that answer your question?
So, what would I find in node B in a normal case?
In node B. In a normal case, this would never have existed,
Okay. So,
and this record would have been copied down to node B.
okay, this is what I was
Yeah.
asking.
So both of these would have UUID 1, you know, X and 0. So they would see the same database record. Yeah, this is sort of the edge case, which should never happen, but it's there to handle the mess, if it does. So anyways, getting back to the table, you know, as you saw, we created with the name, or the database referencing the UUID. This is kind of getting back to your question of, if you create, you know, table Y here and table Z against this one, you can't sort of necessarily merge these two back together, because they're going to have different tables and different data within them. That becomes a process that would need to be probably managed manually, resolve those. But under most cases, like your application could probably have a script that says, hey, somehow we ended up with x.2, just compact them and sort everything out. And that would be like a step of conflict resolution that you would handle in your application. The next step beyond creating a table, obviously primary key is a big one to handle here. And rather than having something like an auto increment, we would basically have a, UUID, or not a proper UUID, but have a, a global auto incrementing ID, which we can use one of these for as well. Since it's 64 bits in most web apps, like WordPress, for example, creates 64-bit primary keys with auto increment. If that were a time-based UID, they're not going to be sequential in their assignment, obviously, and you're going to start at some 500 trillion ID.
Everyone understands that auto increment keys are not guaranteed to be sequential anyway.
Yeah.
Your people have gotten very lackadaisical used to the fact that it's mostly true in NODB, but it's not guaranteed.
Yeah. But, so that's why, since it's not guaranteed, it should be okay to say, oh, instead of, when I create my first row of an auto increment, rather than getting 1, you're going to get, some god-awful number that's, beyond the 32-bit range with some random bits at the end. But at least they're going to be incremented according to time. So you can still sort them according to when they were created, because, the highest order bits are going to be seconds.
I'd like to just toss out that maybe not everybody understands that. I'd say that a lot of the folks out there writing applications think that they're
I kind of phrase it that way.
monotonically increasing from 1, and
Yeah.
if anything happens with that, their entire application breaks.
Well,
Yes.
That's very common, actually.
yeah,
very, very
possibly. And like I said,
I'm not saying it's the right thing for them to think, but
Yeah.
it's their education.
and this will expose some bugs if their first ID is giant number. But
That's why you have consultants that make money out of this.
yeah,
So, being the Berkeley DB guy in the room, the storage engine guy, not the SQL, although we just added that, I'll forget about that.
yeah.
Why did you take the approach of working down as opposed to working up? Why not start with the storage layer and work on multi-master, page-based, record-based storage, and using those as your unit, as opposed to starting with database operations and large database concepts, working down?
Because I saw this is still a fundamental problem. Like, if I were just to write a storage engine for MySQL, you couldn't get the same levels of guarantees that you can with this.
Why not?
Because when you say, create a database, there are things within the MySQL engine that you just can't introduce new fields into the database record.
Right, so I guess the answer is that you're thinking through the MySQL lens, not thinking in general.
Yeah.
Right, so you're going to take MySQL and improve it and make it multi-master, not...
If I wanted to start changing like the database catalogs that are more in the MySQL kernel than in the in the storage engine, then yes, possibly could have gone that.
No, but I mean that I didn't understand. I guess the answer to the question is you chose MySQL as a starting point. You could have easily chosen SQLite or Postgres, or you could have chosen any number of other things, or you could have just chosen something entirely differently. But from a Berkeley DB, guy who's been stuck down at the database engine level, I see a different route for solving this exact problem from the bottom up that would completely alleviate the need for you to worry about it as a SQL database level program.
Yeah, so I probably should have
I
prefixed.
could give you an engine that was like the multi-master engine, and you just forget about it.
Yeah, I probably should have prefixed all this with my original problem that I wanted to solve was the basically a cloud-based multi-master SQL database that works with common web apps. Like I want to be able to run, like the first thing I'm targeting to be able to run on this is like WordPress in a true multi-master fashion. So it needs to speak most likely the MySQL protocol, since that's the most common protocol out there for these types of web apps. I mean, most work with Postgres quite well, but you're probably going to reach a few more people who speak the MySQL protocol.
The test case might be Sugar's CRM as a real exerciser for a database, but
Yeah, but the interesting thing about WordPress is there's no concept of transactions, which I haven't even gotten into the transactions, but basically you have to throw all that away. So if you're thinking about every statement as a transaction, it works quite well in a database like this because you don't actually have to worry about any type of isolation or serializability.
Every statement or every batch?
Every statement.
Every statement.
Yeah, there's basically the MySQL mode is auto commit. You equals true. That's enabled, actually for Drupal as well, it's the same way. Some of their upgrade operations, for Drupal, they do some multi-statement transactions, but for the most part, it is, this insert statement is its own transaction, update, so forth. There's never like, you know, select and update within the same transaction. That pretty much doesn't happen with WordPress or Drupal. Yeah, and the
it's
reason
also
why,
quite frequent in a lot of web apps involved written
Yeah.
targeting NoSQL.
yeah, they don't, actually most people writing PHP or Python web apps don't even understand SQL transactions, so, you know, there's no way to use them.
Yeah.
You know, if you don't understand them.
So back to your use case.
Mhm.
You just want one, so you want a multi-master database, but just one.
What do you mean just one?
I mean, so you just want one instance of a multi-master database with like 2 nodes? I mean,
No,
how many?
I
I mean, do you
want-
want to be able to support like a gazillion user? Because in the end, it all goes back into all of the instances need to be eventually consistent with each other.
Mhm.
So that means one node has to hold all the data for all your users. Or are you going to shard
not
on top?
necessarily. I mean, getting into the semantics of, you know, what gets replicated where and who has what copies. Just imagining a mesh of, say, you know, 50 nodes, and for a particular database, maybe you always want to guarantee that there's at least 3 copies of that database. And, you know, there's obviously a lot of logic you have to write on top of that to say, hey, you know, database X should have, you know, 3 copies. It's, you know, when you create that database initially, you pick 3 nodes and make sure it's on those 3 nodes. If a node goes down, you know, detect that and go to another node. But the idea is to have not just 2, but to have any number that you want, and that's basically configurable by just saying, okay, start pulling the replication tree for database X from that server, and, you know, just start that link up, and having, you know, building the management tools on top of something like this once those abilities are there.
There's just lots of problems that, you know, there's lots of edge conditions that need to be, you know, I mean, in terms of what you just said, like, okay, go grab the replication tree. Yep, that server just went down.
Yep.
You know,
Well, I mean, basically, define the link, and it'll connect when it can. But it is normal operating procedure. Sort of the assumption is that nodes will always be down somewhere, and, you know, be able to handle the cases when they do come back up and resolve all those differences.
I guess I'm just still not clear on what is it what is it you want to get out of, like, what do you want to talk about now? Like the problems with this, or like ways to do it, or?
Well, I was just kind of drilling down. You know, I was going to get into, you know, different types of row updates, you know, transaction handling and replication, and seeing how you can generate replication events that are, you know, like I was saying, both idempotent and deterministic. So you can handle all those edge cases that you're probably ever thinking of.
But if we come back to the original problem that you showed at the beginning, how does this organization solve it?
How does it?
I mean, if I have a conflict like the one that you explained before, when you have something goes into master A, something goes into master B, and then they change. How do you deal with that using this? How does this big organization alleviate that problem?
So basically what would happen, say if we were, you know, just setting the stage of we're in a big multi-tenant hosting environment, and we have these types of, you know, basically as a cloud service, like, hey, give me a relational database in the cloud. And rather than doing like the Amazon RDS type solution where you get a dedicated VM running a database, you get a, you know, this magical service with an API that you can talk to. You know, you start talking to it and you say, create database here, and then at the same time, your application posted over in Europe says, you know, create database with the exact same thing, and maybe those streams haven't, you know, come back over. And if you do that, you're going to basically have the case where you have X and X.T. And at that point, when the replication streams finally make it over, and this detects like, hey, there's already a database created with X, and I'm getting this other one coming in from, you know, the replica over in America, and now we have X and basically X.2. You have that context there, and you know that something is wrong, like something went wrong. And you're going to have the context of who that user is because of, you know, the meta information attached to all this. And you can say, you know, set up account triggers or whatever to say, hey, there's a conflict in your database, go resolve this. And then at that point, you can do it manually, or maybe start building tools to resolve those conflicts within your application.
So the difference would be that I will have the problem again, but at least I will know that I have the problem.
You will know that you have the problem, and depending on how mature things are, you may or may not have a tool to automatically solve that. In some cases, you may be able to have these tools already set up, ready to go, so when you detect that, and you know you can solve this in a sane way, you can just say, call this tool to resolve it. Or you can say, you know, just let me handle it manually, you know, notifying you that something bad happened. You know, it's basically, if you want to design a system like this, you're going to have these types of constraints, and I'm just trying to find reasonable ways to solve them when you start coming up with these edge cases. So, yeah.
So maybe I feel like these are less of a problem, but I'm more interested in what you were saying before, like row updates and making them possible.
Yeah, so, so say we have, so we've created our table Ys, and let's assume everything only has one copy of it, and you know we didn't have any down replication nodes, so it was only created once. So we'll call this replica 1. We'll have a replica 2 over here, and we've created. Our primary key is basically one of these auto-incrementing, of course, not actually sequential. And
Call them auto-unique.
auto-unique, that's a good And we have, say, ID2 on both of these. Actually, that would potentially be, we'll just call it 5. And, you know, say according to the table definition, we have, you know, we have some name, so name is Eric, and there's some value 20. And this one, we'll talk about an insert case, and this is, inserts it with 30. Now, if these are seeing if these are two different replicas, and this creates ID 5 here, and this wants to create basically insert the same logical record, but if it's using a auto-incrementing or auto-unique ID, it's not going to end up getting the same one. It's not going to get 5. So we're going to basically have 2 records in here with, you know, Eric and 20 is the 2 values for the field. But that's okay, because we never said that, you know, this is the unique part. We never said that those 2 things are unique. So we don't have to worry about that conflict. If you wanted this unique, and this basically gets into supporting unique indexes in a system like this, you've probably already guessed that it's pretty much impossible to do. We can't even guarantee uniqueness on a database or a table name when we create it, because there could be another one coming on later on. So when you say like create an index unique, or if you assume that your primary key is always going to be unique, that's really a suggestion. It's not going to be the absolute truth to the system underneath. And basically your applications need to be able to handle this. In the case of something like, you know, getting back to WordPress, I'm creating a blog. I'm probably only going to be doing that from one node, and then it's going to go and replicate out. And I'm probably not going to try creating the exact same blog entry on 2 different sites at the exact same time. Chances are I'm going to be creating a blog on one site that'll replicate out, and I want to update that same blog over, you know, another part of the country or something like that. It's going to pick it up and be able to edit that one with that record. Does that make sense? In the case where you truly, you know, if your application can't handle possible duplicates on a unique, unique now in quotes, key, this probably isn't going to be true. But like I was saying, I'm not thinking about, solving the generic relational database problem. I'm thinking more in terms of, putting the high availability first and just seeing what constraints come, from trying to solve around the problem. I don't know, do you have any thoughts on resolving this type of uniqueness without, in a different way?
Not in my head, no. But that's interesting.
Try the blue filters, man.
Something I know about.
Yeah,
Not sure.
Blue filters are awesome until you start.
but you don't know, you may not even be connected. Like you may have a replication node or a replication link between two nodes down for a day. So it's not going to be.
Bloom filters are awesome to see if you want to check your local physical store for something, but not if you want to cross a data center boundary.
Yeah. I mean, it's great for cluster databases and distributed if it's kind of more of in a lazy way. But when you want to guarantee uniqueness, you need a atomic view of everything in your system, and that just is impossible when you start introducing these types of properties. So. Unique is really just an advisory keyword. If I create, say if the unique was both on the key and the name, and this replication event made it over here, this can say, hey, I already have a key, based on based on those two columns, so don't create it. So unique will be in effect sometimes, but if this link isn't there, this is still going to create another unique row entry.
You had some way of our system knowing that all of the nodes that are expected to be online are online, then you can say that operations that require a uniqueness just aren't available during certain period of operations.
I've thought about that, but the awareness of every node in the system introduces a whole another set of complexities of management of all the nodes. And I like the idea of going down the path of just creating it lazily. Think about if you're familiar with how IRC servers are networked together. Create an IRC network here, and one's here, you link them together, and then they flash out, share the channels, resolve any differences, and we all love the free node net splits that always happen, those things happen, and so forth.
That's because it solves the contention problem by forcing by IRC network as a DAG. There is only one route between an arbitrary point.
Yep, this is exactly what the replication model for this is. You subscribe, it's kind of like an RSS feed. I want to subscribe to this node over here. It's not necessarily the master, but I'm just subscribing to it, and that's where I'm getting my updates. And you could have, that directed edge going between, two ways between two nodes too, if you wanted to. But there's sort of an assumption there that nodes don't know of each other, before the system is set up. I can just join and become a useful part of the system without having to, know the system before.
The problem, also the other problem with knowing all of the nodes is you wind up with the end-to-end impends in lots of network traffic, I should say. Once you get into thousands of nodes, it becomes prohibitively expensive to have everybody know about each other because the heartbeat traffic becomes.
Yeah. Then I was going down the road of looking at different type of route aggregation, like BGP protocol type stuff, and seeing how you could basically apply that to relational databases.
Well, come on, we all want to become experts in BGP to be able to run databases.
Yeah, it wasn't. I went down that path for a few days thinking through things, and I was just like, just keep it simple. We'll just subscribe to it like an RSS feed, and
They're high cost, that simplicity, going back to the IRC model, but that's the reason why splits are so slow to heal now is that when the join happens, the entire catalog has to be transferred back and forth between each side.
And that's another thing I wanted to.
And the catalog in IRC consists of a list of every server, every channel, and every user.
Yeah.
Well, I was going to point out, you kind of solved the insert problem by basically saying, okay, we're not going to these are now two separate things, even if we wanted them to kind of logically the same. But if we do an update that points directly at one of these things, you're now really talking about the same object. And how does that work?
So if you look at the replication record, say I want to change this to 10, and I want to change this to 15, say there's an operation, you know, divided by 2 or something, the replication event would essentially be, and this is probably going to scare people thinking in terms of replicated rows, but keep in mind the use cases for small row data. I'm not thinking like you're going to have, you know, megabyte blobs in here. You replicate the entire row, not just the thing that was updated, not just the field that was updated. And your replication record would basically be updated ID, which is again one of these. So say updated ID 7, this isn't very good, and then RD for your row data. So if this one generated this updated ID, and we'll call this update 8, and this is the row data for that one, every row beyond having its primary key is also going to have an updated timestamp associated with it, and basically take the latest, use like the CouchDB approach of just use the most recent one that you found. It's sort of the extremely lazy way to do conflict resolution with these types of systems, but it's probably going to work for 99% of the use cases that at least I have in mind initially. So that way, this particular update would essentially be lost, and both tables would see the one with the higher update time, which is 8. And the deleted thing basically happens the same way. You know, just have an optional deleted time in there as well, saying this row has been deleted. But you actually want to keep the deleted row around because you may have an update that comes in after it's been deleted, and you want to make sure, you know, that update can be applied, okay, and then at the end you can say, okay, and when the sort of what I'm calling the time window of when things can change, you know, passes, we can say, okay, now we don't have to worry about any more updates or other things coming in modifying this row. We can actually physically drop it, but it's not going to be necessarily dropped immediately because other events could still come in if we were to do that immediately. So.
Tombstone.
What's up? Yeah.
Tombstone.
Yeah. Yep. Yeah, and does that, any other questions on like?
I just wonder if it would, if going from a different point of view of trying to put like a SQL layer on top of something very like MySQL-ish at all. I mean, at this point, we've lost really almost all of our kind of benefits, as it were, of a database. Other than that, we still have like data that looks like it's in the table, in a lot of ways.
Pretty much.
And so the real benefit is having a SQL interface that we can just say, okay, WordPress, go over here.
Yep.
One program
that's
going to create neat update.
Sure, absolutely. I mean, there's a lot of value in that, but I wonder if, I mean, it's good, totally speaking out loud, but if there's benefit in instead trying to have like a SQL interface on top of something like MongoDB or whatever that might have enough strength to its model that you could do something like this instead of, I don't know, it seems like it's coming from it's like,
obviously before,
sorry.
Obviously before going down this path, you know, I looked at things like Mongo and CouchDB and so forth to see, could you just slap a SQL layer on top and get the same thing? And you really can't, because the context of knowing that you're in a relational database and this is how your data is structured, you can do things a lot more sanely and efficiently than if you were trying to put that on top of like a document store database. You know, the semantics are slightly differently. Like the idea of creating databases and then tables belong to a data or a catalog and then having row IDs and having all the semantics is just, it wasn't enough of a matchup. Like there would be so many modifications to one of those projects that was like, well, why even start with it?
One of the other problems too is you wind up the work to implement a SQL optimizer and query plan, like thing to slapping a SQL layer on top of Mongo, probably a much larger task than it. Like it's one of those where it sounds really easy. Because I started down this road a little while ago, and I was like, oh Jesus, Like, there's all of this other stuff that I've forgotten is
I
there.
myself have started 3 times putting MySQL on top of Cassandra, and
So
we
almost
put
matches up.
SQLite on top of BurkeDB. BurkeDB has replication, single master multi-reader. That replication can be configured in other ways so you have multi-master. So now, what's the difference there? I mean, yeah, it's not got all of MySQL semantics.
Well, so why don't we bring back the BurkeDB storage needs?
Why not?
So
I
people
know
have
the
actually,
Visual project takes patches.
so people have actually written SQL to Mongo translators for subsets of SQL or all of SQL, but using Mongo in a very funny way. So it's doable, but it's not going to be optimized particularly effectively.
That's
Yeah,
my,
it's not a natural fit.
that's
No,
my,
but
that's
I
my-
mean, people have done it as a drop-in to use
Yeah.
Mongo as a drop-in replacement for MySQL underneath things that they have.
Yep.
Yeah, but Mongo isn't multi-master. It's not multi-master, no.
Yeah.
That's my experience putting MySQL on top of Cassandra, is every time I went down the path, I ended up torturing Cassandra into shape. There wasn't any way of, starting with the Cassandra set that someone had built for an application, and saying, oh, let's put an SQL layer on top of your existing Cassandra implementation.
Yeah.
I'm
I
still not
mean, it's-
following how you would do a join in Cassandra or MongoDB.
Don't do that then.
Exactly.
Yeah.
Well,
Yeah.
from the database's perspective, it doesn't look like a join. It'd be a
You'd have to
client layer.
parameterize it.
Mhm.
Yeah.
We just tell the programmer, don't do that.
It's why joins in MySQL cluster on top of NDB are expensive.
It's,
Because you're doing a
Across
nested loop
network.
join across the network.
Yeah.
It works. If you can do it.
push down conditions.
Well,
Don't.
don't we have the same problem here if we're talking about tables that are on the same server, or are we?
No, a particular table or a particular database is entirely, it's all contained on the same server. You don't have to worry about touching anyone else's.
So this doesn't
Copies.
have sharding or anything kind of involved in that?
I mean, you could put sharding on top of it, but
Right,
initially,
then you
no,
have the
like,
same sharding.
yeah, yeah. The other thing is, this is, obviously, looking at the type of replication events, if we're shipping the row data, this isn't something that you want to do with like extremely large tables with, high turnover rates and high update rates. Like, this is something where,
This is more about HA for smaller data.
yeah, this is, I want to host, 10,000 WordPress blogs, and each one of those databases for those blogs are going to be, 2 megabytes, maybe, maybe 10 megabytes after, they've been picked up by a decent plan or something like that. So it's going to be pretty small amounts of data, and most of it is probably just going to fit in memory too. And obviously those joins, you can do pretty sloppy because it's going to be the assumption that you're working with pretty small data sets.
So in the next, the next release of BurkeDB, we're going to do update shipping from read-only replicas back to master and then applying across. We have peer-to-peer replication. We are an old MySQL plugin. It would probably, we actually, in the midst of the InnoDB/SleepyCat acquisition, we highly optimized BurkeDB to fit in there and become the successor, but then things happen. We've got a friendly open source license. Why not that? Well, I mean, for your use case, we're done in a week. I can get you running in a week for your use case. Multi-master, very close to
No,
multi-master.
I'm not.
I guess I'm
just-
asking, like, why
Yeah.
have you? You're right. This is a very hard problem. What you start doing when you start going down this road is giving up pieces of what you would want from relational technology, what you've been guaranteed in the past,
Yeah.
in order to get some of the features that MongoDB has made popular.
Yeah. So as far as the actual, practical side of this, programming this, from scratch, because I didn't find anything, at least on some of the layers to really start from. Like, obviously the storage engine layer, I've already talked to, like the guys from PBXT storage engine, and they want to potentially try to plug this in. And BurkeDB might probably be a pretty good solution as well.
Honestly, my thing is I had no idea that BurkeDB even had replication.
So Google accounts up until about a month or so ago ran globally multi-thousand node BurkeDB replication. So everybody, what?
Synchronous or asynchronous?
Synchronous. Synchronous, and you can configure it to be asynchronous at your leisure. So if
Yeah,
you
but
like,
the problem is when you are asynchronous, then you have conflicts. When it's synchronous, it's easy to fix the conflicts.
yes.
It's not particularly easy to scale it out to
That's
thousands
eventually
of nodes.
Right, so, but every time you log into any Google property, Google accounts, up until a few months ago when I switched over to something
And it
like
started sucking.
What?
And it started sucking.
Exactly. That was Berkeley replication. Right now, every time you log into Steam, if you're logging into Steam, you're logging into Berkeley DB. We're an old database technology with lots of tricks and really crappy marketing. And I call them.
No, so one of the, in my last couple jobs ago, I worked at,
Yeah,
like we
I
built,
thought you were a SQLite without the SQL.
and we built a database. It was kind of like an object store database with metadata. And it wasn't SQL based at all, and it was clustered and so forth. And we used Berkeley DB because it was, you know, pretty rock solid. And we wrote that in Erlang and, you know, put the Erlang API on top
I
of it.
remember this, yeah.
And everything worked really well. So I'm certainly not opposed to it. I just haven't gone down that path yet of exploring this because I'm still in the, not thinking about the data store on this. Like, I'm just thinking, like initially I was doing a lot of the work in Erlang, or actually the first prototype was in Python just for conceptual, like, would this replication model even work? Yes, it does, but performance is god-awful. I can't continue in Python because of speed constraints.
Right.
And then I had another project in C++ that I was doing, hoping that I could get it to the point to start working on some of this real work, but the development time, especially for, you know, a part-time project just wasn't there with C++, it was too slow. So finally I chose to go back to Erlang, so I still have a lot of that old code that's still tied in with Berkeley DB, so it may be something that I do later on.
I mean, your initial, the premise for the talk was, can we do a NoSQL, you know, can we bring this NoSQL kind of benefit to the NoSQL world? I think the answer is absolutely yes. I think, you know, this is a great, I like your approach, you're using different techniques. A lot of this already exists in different ways. We narrowed your use case down to like, okay, I'm giving a small amount of data, everybody send an entire copy, you send it, it's exactly what it's supposed to be. If you grow your case out to the Mongo, I have shards and they live everywhere. Now you're getting into a space that we can't cover yet.
Yeah. So, yeah, and I admit this is completely unoriginal in a lot of ways, and it's just slapping together other ideas, and yeah.
That's always a great art skill, right?
Yeah. So yeah, definitely am going to take a closer look at Berkeley DB. So I'm assuming we're
under MySQL again.
That's retarded. It won't under,